Hello everyone, and welcome to my channel. This is a channel for educational purposes, and we tend to take a look at a lot of theories of everything, do deep dives on all-encompassing cosmologies that you probably never heard of, or if you've heard of them, you don't know what they say, and we're trying to provide you with the details so that you can make your own decision before the academic establishment just bans it outright and doesn't let you know about what it actually says. And today is our 423rd video that we've done on the reciprocal system of theory from Dewey B. Larson. Mr. Larson was an engineer, and around 1959 he proposed his two fundamental postulates. Just two sentences about how he believed the universe operated based on decades worth of condensing inductive work that he did before that. And then he switched it around and through a process of deduction went from his two fundamental postulates to a theoretical universe. So he went through, it's called the outline of the deductive development of the reciprocal system, which I covered about a year ago in about 15 videos. And so he proposed his theoretical universe about what his universe would look like if his postulates were correct. And then from there, he wrote books kind of comparing his theoretical universe with the empirical measured universe of the legacy scientists that they've developed in their laboratories and observatories and so on. And we're looking at an example of that today from the field of chemistry. This is Larson's book, Basic Properties of Matter, where he comes up with equations, theoretically, comes up with equations for the different basic properties of matter, such as the interatomic distance and the compressibility and the specific heat and the melting point of different elements and compounds. And we are doing our second installment on chapter 3, which is called Distances and Compounds. This is on interatomic distances in chemical compounds. Now, the basic thrust of Larson's reciprocal system, which is fairly aptly named, but also you can call it the universe of motion. Larson's universe is a universe of motion. So his universe is built upon motion, not matter or not energy or force, the fundamental forces or anything. It is built upon motion. And for Larson, motion, he's referring to really a specific kind of motion that he calls scalar motion. This is a more generalized and non-localized kind of motion that has no direction. It's got a magnitude but no direction, that you can visualize using a balloon that you put dots on. As you blow up the balloon, all of the dots will be moving away from each other. And but they're not moving in any specific direction. If you suck in the balloon and the balloon contracts, then the dots will be moving toward each other. But again, in no specific direction. And these are what Larson calls the progression. The outward scalar motion is the progression. And the inward scalar motion, maybe among other things, would be analogous to gravitation. these are the two fundamental motions. Primarily, the outward progression is what the universe is built upon. So reversing that progression is kind of like how you get to things like matter and so on. Also, energy. And the other part about motion that has kind of precluded other scholars from successfully employing it as their fundamental in the universe is that Larson defines motion in a different way. He defines motion as the relationship between space and time. That brings about a generalized reciprocal relationship between space and time. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. So the simplest example of motion that we can get is speed. The bicycle is moving 15 miles per hour, 15 miles of space in 1 hour of time. Space over time is speed. And you can see the reciprocal relationship if you decide to double the speed. You can now say, now the bike is going 30 miles an hour, doubling the space in the same time. Or, equivalently, you can say the bicycle is now moving 15 miles per half hour, leaving the space the same and having the time. So they're both equivalent. You can either multiply one by 2 or divide the other by 2. And now if we look at the inverse of that, time over space, that is energy. It took me 3 hours to push that thing 1 mile. 3 hours of time and 1 mile of space. And all of our other scientific quantities are also different forms of motion. Matter is time to the third power over space to the third power. And that's something that Larson brings to the table with the reciprocal system also. He posits a three-dimensionality of both time and space and motion. So we generally perceive space as being three-dimensional, but he's saying that time is also three-dimensional, or at least it has a component that is three-dimensional. And then Larson also posits the discrete unit postulate that time, space, and motion come only in discrete units. I don't know if before I said time, space, and motion all have 3 dimensions. I might have said matter, but I meant motion has 3 dimensions. And time, space, and motion all have come in only discrete units. You have to have a minimum unit of space and a minimum unit of time before you have space or time. And therefore, you have, if you have 1 unit of space in 1 unit of time, space over time being speed, you get what Larson calls unit speed. And this unit speed turns out to be the speed of light. And this is the background speed of Larson's universe. In order to accept Larson's universe of motion, you have to be able to conceive of motion without anything moving. Motion precedes the thing that's moving. And so in Larson's empty universe, you still have this outward progression at the speed of light. That's what Larson refers to as the progression of the natural reference system. This is omnipresent and eternal. It's always there, and he refers to this as the natural reference system. So this is the system that nature conforms to. We generally conform to this stationary reference system where we make our measurements from zero motion. But Larson, in the reciprocal system, makes his measurements from unit motion, from outward at the speed of light in all directions. So when Larson refers to speeds, he's really referring to speed displacement, the amount that the speed differs from speed outward at the speed of light in all directions. Now, another thing is that that unit speed outward in all directions is the midpoint of the universe. So half of the universe is moving faster and half is moving slower. And so this unit speed is a kind of a boundary between two different sectors of the universe, which Larson calls the material sector, moving slower than light, which is the sector that we're familiar with, and the cosmic sector, which we're not so familiar with, which is this sector that is moving faster than the speed of light. These are inverse relations, reciprocals. In the material sector, we have our relationships are based on 3 dimensions of space in a still frame. Larson calls that coordinate space, or the spatial reference system, Euclidean geometry. And then so we have 3 dimensions of space, and we have what he calls clock time. This is a scalar motion in time, like on the surface of an expanding balloon. Time is always getting farther and farther and farther apart, or I guess you could say later and later and later. When you cross that boundary and move into the cosmic sector, then you have relationships based on 3 dimensions of time, coordinate time, which maybe is like polar Euclidean, and clock space. Space is moving in a scalar manner, always getting farther and farther and farther apart. And this is really like your temporal, your time reference system. And then within each one of those sectors, the material and cosmic sectors, you have an inside region that in the material sector, Larson calls it the time region. This is the region that is where the interactions occur in less than 1 unit of space, the microscopic. A unit of space is 4.56 times 10 to the minus 8 meters. So this is 1/500,000th of an inch. So in spaces less than that, you don't have a full unit of space. And so by the discrete unit postulate, you don't have space. So you only have time, because the contents of the universe is space and time, or motion. And so Larson calls this the time region. And when you cross that unit space boundary, you move into the time region, and the rules reverse again. And instead of the progression moving outward and gravitation moving inward, you have gravitation moving outward and the progression moving inward. And so these are kind of the dynamics that Larson, and the same thing occurs in the cosmic sector, except with time instead of space. If you get to less than 1 unit of time, then you don't have time, you only have space. Larson calls that the space region. That's the realm of cosmic atoms and cosmic particles, cosmic compounds. And so this is kind of the realm where Larson is dealing with this chemistry. in particular the interatomic distance. So theoretically, Larson figured out that the interatomic equilibrium in the solid state is established at the point where gravitation moving outward in the time region is equal to the progression, which is moving inward in the time region. And where those two places are equal, that is where the equilibrium is established. Now, the progression is constant. It's always there, omnipresent and eternal. And so this is the point where gravitation, which is variable based on an inverse square law, is equal to the progression. And so that is kind of how he sets up his equations. And so now we're looking at distances and compounds. The previous chapter had to do with interatomic distance, just in the elements. But now we're dealing with the compounds. And Larson does kind of, you know, this is pretty specific stuff. So you might want to go back and listen to, you know, my previous 14 videos or so, if you want to get all the details of this. But we will we'll take over here and see where Larson goes. The dimensional inactivity in the lower groups, like the lower groups, the bottom of the periodic, or the top of the periodic table, elements 1 through 10, plays only a minor role in the structures of the elements, in the structures and the interatomic distances of the elements. At those low elements, sometimes only 2 out of 3 or 1 out of 3 of the dimensions, again, these are scalar dimensions, not directional, are in play with these lower elements, as can be seen from the fact that it did not need any attention until almost at the end of table 8. So Larson calculates the interatomic distance for, he calls them the calcium fluoride type compounds. So calcium has a valence of 2, fluorine a valence of 1. So this is still an ionic compound. I guess there's a difference between this and the NaCl group, just because of the extra atom and the extra valence there for calcium and the extra fluorine atom as opposed to NaCl. You know, he's calculating the interatomic distances based on these specific rotations of the atom. You know, the atom is based on 3 scalar rotations, 2 two-dimensional rotations that alternate, and one-dimensional rotation that is in the opposite scalar direction. You know, these are all built upon the original 2 photons that are at the core of the atom. And he calculates in angstroms. So we've got disodium oxide. I'm just guessing at the names of this. Na2O. Calculated at 2.39. Observed at 2.40. Disodium sulfide, calculated at 2.83, observed at 2.83. Disodium selenide, calculated at 2.94, observed at 2.95. Disodium, I don't know what Te is, tellurium or something. 3.13 observed at 3.17. Dimagnesium silicate, I don't know what that compound is called, but Mg2Si, calculated at 2.73, observed at 2.77. Mg2 germanium, that is 2.76, observed at 2.76. And on. He provides another 20 or so. And it looks like they're all within 1% of the experimental value, except for one here, which is off by about 2% for, I guess that's maybe strontium chloride. As you can tell, I'm not a professional chemist here. It looks like he's way off here. No, he's close. I misread that. Okay, the compounds of lithium with valence 1 negative elements follow the regular pattern and were included in table 7. But the compounds with valence 2 elements are irregular, and they have therefore been omitted from table 8. As we will see in chapter 6, the irregularity is due to the fact that the 2 lithium atoms in a molecule of the CaF2 type, calcium fluoride, I guess, CaF2 type, act as a radical rather than as an independent constituent of the molecule. I'm struggling to remember what a radical was. I know it's a square root in math. It's something like that in chemistry too. These 2 normal orientation tables, 7 and 8, provide an impressive confirmation of the validity of the theoretical findings. One of the problems in dealing with the interatomic distances of the elements is that because of the relatively small total number of elements, the number to which any particular magnetic rotational combination is applicable is quite small, and consequently it is rather difficult to establish a prima facie case for the authenticity of the rotational values. But this is not true of the normal type compounds, as they are more numerous and less variable. There are 2 elements in these tables, sulfur and chlorine, that have different magnetic rotations under different conditions. These elements have 4-3 rotation. That's 4 primary 2-dimensional rotations and 3 secondary 2-dimensional rotations. These elements have 4-3 rotation in the calcium fluoride type crystals, and in the sodium chloride type combinations with elements of group 4A, in the other compounds of the NaCl type. They take the 3.5 rotations. When he says half like that, it means that the rotation, it's not, the reciprocal system is quantized. So you shouldn't have fractional values. He uses that notation, 3.5, to indicate that basically the rotation is whole, but it's being split by these 2 different rotations. So it's not that there is half a rotation. Although when he does have the atomic rotation, that is equal to a double unit. So I suppose it could be split on that basis as well. In the other compounds of the NaCl type, they take the 3.5 rotations. There are also 2 more elements, each of which, according to the information now available, deviates from its normal rotations in one of the listed compounds. Otherwise, all the elements entering into the 60 compounds in the 2 tables have the same specific magnetic rotations in every compound in which they participate. Furthermore, when the inherent differences between the elemental and compound aggregates are taken into account, there is also agreement between these rotations in the compounds and the specific rotations of the same elements in the elemental aggregates. The most common difference of this kind is a result of the fact that the division 4 element in a compound has a purely negative role. For this reason, it takes the magnetic rotation of the next higher group. In the elemental aggregates, half of the atoms are reoriented to act in a positive capacity. Consequently, they tend to retain the normal rotation of the group to which they actually belong. For example, division 4 elements of group 3A, germanium, arsenic, selenium, and bromine, have the normal specific rotation of their group 4-3 in the crystals of the elements, but in the compounds they take the 4-4 specific rotation of group 3B, acting as negative members of that group. Just to let you know, maybe give you a little bit of encouragement, I pretty much don't really know what he's talking about here. He's gotten into pretty specific territory, and this is, you just kind of read over this to just kind of see his thinking a little bit and get a sense of what's important to him as he goes through this. But as a generalist and as somebody who's just trying to pick up the theory, just let it wash over you, and you might pick up a tidbit here or there. You might be able to store some things in the back of your mind that you can employ later. Again, this is all like a detective work. You're just trying to pick up clues, a few clues at a time, a few breadcrumbs at a time, and you'll have to put it together later. So, but I do want to let Larson's own words speak, in case somebody is really chemically inclined and maybe can go into the weeds here with this. Another difference between the two classes of structures is that those elements of the higher groups that have the option of extending their rotation to a second vibrational unit are less likely to do so if they are combining with an element which is rotating entirely on the basis of vibration 1. Aside from these deviations due to known causes, the values of the specific magnetic rotation determined for the elements in Chapter 2 are also generally applicable to the compounds. This equivalence does not apply to the specific electric rotations, as they are determined by the way in which the rotations of the constituents of each aggregate are oriented relative to each other, a relation that is different in the two classes of structures. This applicability of the same equations and, in general, the same numerical values to the calculation of distances in both elements and compounds contrasts sharply with the conventional theory that regards the interatomic distance as being determined by the sizes of the atoms. So, the conventional theory is that these interatomic distances are the sizes of the atoms. In Larson's system, they are not the sizes of the atoms. They are the structure, the bonding, how far apart are the atoms. The atoms are much smaller than than is being contemplated by the conventional theory. The sodium atom, or ion, as in the NaCl crystal, for example, is asserted to have a radius only about 60% as large as the radius of the atom in the elemental aggregate. If this atom takes part in a compound which cannot be included in the ionic class, current theory gives it still a different size, what is called a covalent radius. The need for assuming any extraordinary changeability in the size of what, so far as we can tell, continues to be the same object is now eliminated by the finding that the variations in the interatomic distance have nothing to do with the sizes of the atoms, but merely indicate differences in the location of the equilibrium between the inward and outward forces, the progression and gravitation, respectively, to which the atoms are subject. Okay, so he's kind of pinning down the legacy scientists, saying, well, you know, with your idea that these distances are the sizes of the atoms, then depending on the kind of bonding that's going on, sometimes the atom is only like half the size of what it would be under other conditions. And this is just not consistent with you know, reality. You know, you can put these elements under incredible amounts of pressure and they don't compress, you know, that much, not to like half the size. Okay, another type, unless you're talking about like a white dwarf star or something, a pulsar or quasar. Another type of orientation that forms a relatively simple binary compound is the rotational combination that we found in the diamond structure. As in the elements, this is an equilibrium between an atom of a division 4 element and one of a division 3 element. And again, these are division 3 and 4 are electronegative. Division 4 is less than 4 or less valence, and division 3 is greater, 4 greater valence, or 5 specific rotation. The requirement being that T1 plus T2 equals 8. Obviously, the only elements that can meet this requirement by themselves are those whose negative rotational displacement valence is 4. But any division 4 elements can establish an equilibrium of this kind with an appropriate division 3 element. Okay, we're going to stop there. Keep hanging in there. We'll get back to talking about this tomorrow. Thanks for tuning in.